Today we're going to take a look at something called reaction mechanisms. If we take a look at a balanced equation, what a balanced equation does is it tells us what reactants we have and what products are going to form. Okay, that's the general idea behind the balanced equation. We could also use the stoichiometry of the balanced equation to tell us how much we have. But that's pretty much it. All we know from a balanced equation is what we start with and what we end with. What the reaction doesn't tell us, the equation and the reaction doesn't tell us anything about how it goes from reactants to products. We have really no insight into that based on just what is given on the balanced equation. So there's essentially no information on how a reaction is going to be produced. And that's what the mechanism is. It's a proposed idea of what we think is the step-by-step process on how a chemical reaction occurs. Okay, so that is the mechanism, the step-by-step approach. So if we take a look at this reaction here, we've got nitrogen dioxide reacting with carbon monoxide. But if we look at the experimental rate of reaction, what we can tell from the rate of reaction, from the differential rate law, is that if I change the concentration of nitrogen dioxide, I can change the rate. And what that means, I double this, then we know that, right? This is going to go up by an exponential value. But the question is, why doesn't carbon monoxide have any effect? Now, if we think about chemical reactions, we kind of think about the nitrogen dioxide and the carbon monoxide coming together to create the products. And based on the rate law, that doesn't look like what's happening, because if you think about it, if I put this nitrogen dioxide in the container and carbon monoxide, and they both come together to make the products, then they both should have an effect on the rate. If I double the amount of carbon monoxide, there should be enough carbon monoxide to react with more of the nitrogen dioxide to cause the reaction to speed up. But there's something going on that tells us that the carbon monoxide is not readily reacting directly with the nitrogen dioxide. And that's how we can use our rate laws to get some insight into what's going on in our chemical reaction. And let's take a look at the burning of octane. All right, burning of octane, according to the balanced equation, we need 2 of these molecules to react with 25 molecules of oxygen. How likely is it that 25 molecules of oxygen are going to collide exactly with 2 molecules of octane? Not very likely. So we have a not very good probability of that happening, and that's the idea. The balanced equation just tells us that this is what we start with and this is what we end with. There has to be something else going on in these reactions, and that's what the mechanism is going to do. Now, our mechanisms are broken up into what are called elementary steps. Okay, elementary steps are what we say is actually happening. Okay, we say that this is the actual step that is actually occurring, that these two particles in the elementary step are coming together to make those products. Okay, unlike with the overall balanced equation. Sometimes the overall balanced equation can be the elementary step, but not very likely. Okay, so the sequence of elementary steps, when we put them all together, that's going to give us our mechanism. Okay. Now we have to remember that our mechanism that we come up with is our ideas. This is our explanation of what's going on, and it has to match the observable experimental data that we have. So if there's no consistency there, our mechanism is wrong, and that's what we're going to look at in proving whether these mechanisms are possible. Okay. So here's an example. So let's say we look at the nitrogen dioxide again, combining with the carbon monoxide, and gives us this rate law. Now here's a possible mechanism, and the mechanism is the step-by-step approach of what's happening in the reaction. So we're saying that 2 molecules of nitrogen dioxide come together first. This would be our first step. So instead of these 2 coming together and forming products, these 2 actually collide together to create nitrogen trioxide and nitrogen monoxide. Now this is an elementary step. This is not the overall balanced equation. It's an elementary step. So we are saying that this is physically, literally happening. And therefore, we can write a rate law without any experimental data. I know this kind of contradicts what I said before, but what I said before was that you can never get rate laws from balanced equations. And that's true if we're talking about the overall process. The overall process, we cannot derive this rate law from the balanced equation. But we can do that with elementary steps. Why? Because we are creating these elementary steps. We are writing these from the top of our heads with some basis of the reaction, of course. I mean, it's not just completely, nonsense that we write. So we're saying that these 2 molecules collide together, therefore their rate would be squared, right, with the concentration of the nitrogen dioxide. Because if I double the nitrogen dioxide, I'm going to double them both, so the rate will go up by 4. So elementary steps, I can write the rate law directly from that. Then we can say that that nitrogen trioxide, which doesn't show up in the overall reaction whatsoever, right? There's no nitrogen trioxide at all, then collides with carbon monoxide, and that oxygen is now removed from the nitrogen trioxide and put into the carbon monoxide to make CO2. Okay, and notice what happens here is that the nitrogen dioxide that I have here and here are going to cancel out, and I'll talk about that at the end. But again, I can write another rate law for the second step. So our elementary steps, we'll talk about later, are going to actually add up to the overall reaction here. So in the end, this nitrogen trioxide that started out gets used up. That's what's referred to as an intermediate. Okay, it's something that shows up in the middle steps, but then gets consumed later, is known as an intermediate. Okay. All right, so let's take a look at what we need to do here. All right, so the elementary step here is written. Okay, so each of them is basically, each of the steps is considered elementary, and it has its own rate laws. So as I was saying before, it has its own rate, so we can go ahead and write those rate laws. Now if we go back to, bear with me here, we're going to go back to this rate law. Now the rates of these two reactions aren't necessarily going to be the same, right? Because one reaction might be faster than the other. So if this reaction were really fast, then I would get this constant, I would get a buildup of the nitrogen dioxide. If this reaction were really slow, this reaction can't work until it gets the nitrogen trioxide. So our reactions are always dependent on the slowest step. You cannot be faster overall than the slowest step in your process. Okay? So that's the idea. That's what's referred to as a rate determining step. The rate determining step is the slowest step in the process. Okay, so that's going to be crucial when we try to look at coming back to the overall rate, like how fast the reaction is going. It's going to be based on our rate determining step. All right. Okay, so let's take a look at this. What is known as molecularity. All right, molecularity tells us about how many particles are coming together at any one time. So if I have just one reactant, I would say that this is a unimolecular reaction. Okay, if it's two reactants, it's bimolecular. And in three reactants, we would call it termolecular. You have to necessarily refer to these names, but what we're going to talk about is the fact that uni and bimolecular reactions are by far more likely than termolecular reactions. Okay, so if we have a mechanism, we can come up with a bunch of different mechanisms, right? Everybody can come up with their own mechanism as long as it meets certain criteria. But which one is more likely? Is it more likely that two reactants are going to come together or three reactants are going to come together? So you always want to try to shoot for a uni and a bimolecular reaction. All right, you're never going to have to come up with these mechanisms, by the way, so don't sit there and start freaking out like, oh my gosh, I have to derive or create these mechanisms. You are not going to have to do that. What you are going to do is they're going to give you mechanisms and you have to prove whether they're valid or not. And the way you do that is you're looking at these two requirements. So for a mechanism to be successful or to be acceptable in science, it has to do one of two things. Well, it has to do both of these things. It has to sum up the elementary steps to give the overall reaction. So when you combine all of the steps, you should get the overall reaction back. And number two, the mechanism has to agree with that experimental rate law. If it doesn't do that, then we know that the reaction mechanism cannot be possible. So we're looking for these two tests is what you're going to do. And I'll show you in the next video how we're going to actually do that. Okay, so watch the next video and I'll show you how to apply these two rules to various reaction mechanisms. Thanks a lot.